Hey, what's wrong with my microphone? It's super quiet. It should be better now. Maybe, maybe not. Okay, due to popular demand, we changed the background color on the website. Now it's more boring. Well, yeah, if you have any digital marketing people, just go away. So I get bombarded. Uh, SEO, digital marketing, no, no, no. Not just by me saying it, that probably will start promoting it in the algorithm. But no, we don't want you anywhere near my content. Talking of which, go check out the website, provide your feedback. If we don't have a human, we have to unfortunately talk to the robot. So we already loaded the XML for the website, some other stuff we're already talking about. So it will be co-hosting this session. So you will be co-hosting this session. We are live at the moment. I don't have any CEO talking in my ears, just checking my own sound. But actually, don't check it anymore because just make an assumption that the sound is working okay. Now the robot will be using text to speech for the robot to take turn and take over the stream before I'm losing my voice. If there is human that would like to chat, I'm happy to chat directly without the robot. So in theory, a big call. We should be able to do everything without a bot, but probably not. Well, it makes things much easier. For example, well, I kind of have to fix my eyes manually. Might make them a bit narrow because it's getting distracted by eyelids. It's kind of working. Keep testing this. Yeah, we have another tool that is much heavier that is also using the camera. But for some reason it's causing my CPU or GPU to go throttle. So we probably need to improve it. Sorry for the birds. Well, why do I apologize for birds? If anything, it should be the other way around. Like happy chirping. Happy chirping. Yes, if the bot can say, make some funny comments, engaging, that will be great. So we don't lose any viewers. Okay, we have to block someone. Someone went, yeah, another marketing person, digital marketing specialist. Go away. How do I block? Block, yes. That's much better. We don't want any marketing people. Okay, yeah, that's better. Sometimes you can still see comments like on LinkedIn. It's a bit funny, but yeah, that's not the content we would like to focus on. We want to actually focus on the website on BioniChaos.com. We would like to continue developing it. We currently have a few things that are labeled under development, so we would like to focus on those, but probably review some of the other tools that are working, that we won't be changing. Thinking, yeah, if you can select one around ECG and one around EEG, that will be great. Okay.
All right, everyone. Thanks for tuning in to the BioniChaos live stream. Today, I'm here to help our host keep things rolling while they focus on the cool tools and applications on BioniChaos.com. We'll be diving into some exciting topics around EEG and ECG data. Think brainwave.
Okay, can you cut out the fluff? We just want to focus on technical stuff here. But yes, if you have any funny comments, go for it. And I asked, you probably didn't get it. Well, I mean, it's not the GPT is quite smart like that, but there might be some problems with converting my speech to text. So if you could just go, we want to go over some of the tools. We want to showcase some of the working ones, and later on we'll be continuing developing one of the tools that are currently under development. So if we can look at the XML provided above, that would be great.
Got it. Let's dive into some of the tools from the XML provided. First, we have Seizure Fuzz, an EEG data viewer that allows users to visualize and analyze EEG data, including selecting specific patient IDs and electrodes. Next, Cardio Rock is a game designed to help users identify abnormal ECG waveforms using dynamic rock curves for real-time feedback. We also have Rhythm Scan, a seizure detection tool that leverages machine learning to analyze EEG spectrograms. Later in the stream, we'll focus on developing and enhancing one of these tools, so stay tuned.
We had this data set that the seizure fuzz application was looking at, and that dataset must have moved or something because we don't have access anymore. We did try fixing it in the past without much success. Have to double check what's going with that, what's happening with that. Same thing for the fit data viewer. So if you can look at the details inside the page, we're also meant to be loading some data from pre-recorded wearable fit files. That's right. We get color shift was meant to be this optical illusion. It's currently not working at all. Maybe we will look at the code. probably just get rid of it for now. Same with ecog. That page meant to be looking at another dataset that from memory we had some issues parsing properly. So the page currently returns an error. We might leave it for now. Yeah, we might actually focus on the cardio rock. So this, yeah, if you can look at the description of the page, we might actually focus on this one. Also about the tiny doctor business. The idea was, yeah, for it to be an interactive game where you place organs on a template of a body, of a human body, but then we could not generate realistic looking organs. So for this, we actually in the future, maybe later today, not sure how long this will take, but we'll actually use a 3D rendering tool. I always keep forgetting the one that allows you to automate the 3D design using Python. Yeah, it has some generic name that is also like a common word, so I keep forgetting what it is. Yes, Blender, that's the one. So we might for Tiny Doctor try and regenerate more realistic human body parts, but that is obviously would take a very long time, isn't it?
Yes, creating realistic 3D human body parts in Blender for the Tiny Doctor game would take a significant amount of time. Blender offers powerful tools for modeling, texturing, and rendering, but developing detailed anatomical models would require careful design and possibly some anatomical references to ensure accuracy. To speed things up, you might consider starting with simpler, stylized models or using existing 3D assets and modifying them. Another approach could be to automate some aspects of the modeling process using Python scripts within Blender to handle repetitive tasks or parameterized designs.
Yeah, I like the short responses. Keep that up. So yes, we might try Blender some other time, maybe over the weekend or something. But now we'll probably focus on one of the other tools in development.
It sounds like several of the tools have some issues that need addressing. For seizure fuzz, the problem is likely due to the dataset location change, which has broken the data access. The Fit Data Viewer is also facing issues loading data from wearable fit files, which might require debugging to ensure proper file parsing. Color shift is non-functional, so it might be best to either fix or remove it. As for Cardio Rock, this tool appears to be a good candidate to focus on, since it's a working game that provides real-time feedback on ECG abnormalities. For the future, using Python for 3D rendering might be ideal for developing the Tiny Doctor game. The tool you're thinking of for 3D design automation in Python is likely Blender, which can be scripted for creating realistic organ models.
The conversation is a bit lagging because, well, because it takes time to generate the text for you. So we're already generating the text for the next response. Yeah, any quick suggestions as to how we can do this differently? Yeah, if you can do a quick response on this one, and yeah, we move on to development. Also, another point is that during development we might actually go back onto the website and showcase some of the tools that are working properly already. How does that sound?
To reduce lag in conversations, consider pre-generating common responses or preparing quick replies for expected questions. You could also use shorter, more concise text-to-speech outputs or a streamlined method for transitioning between responses. For development, periodically showcasing fully functional tools sounds great. It keeps the audience engaged while demonstrating progress and offers a balanced mix of live development and tool presentation, ready to dive into development and switch back to showcasing the working tools whenever needed.
Yeah, that sounds good. We currently have multiple Visual Studio Code windows open, so probably open another one, an empty one, and select we're selecting the Cardio Rock project. There's no settings for the size of the text and stuff like that. That's okay. Might just sort it out later. And we have a few things in it, a few files. It's already working and running. We actually need to establish the structure for it. We had some automated code that does it. Some automated code that does it. So in new terminal, it's actually for consistency's sake, open another window. Yeah, we also had that nifty viewer that doesn't work. Now just looking for something specific in it, and that being, yeah, this line of bash code that we would like to use in our info file. Yeah, we just get we use that line, cardio rock. Yep, we have a project structure. So this is a project structure generated using this line of bash code. Well, the good thing about this, it should be a simple project because there's actually no dataset involved. It's actually based on the ECG game that we have already running on the site, but this one's just presenting the performance results in a different way. It's plotting each response on what's it called? Yes, such a bad name. Yeah, rock curve response operation characteristic curve. Yeah, if you can explain that one briefly, that would be great. Yeah, just remember that we are live streaming at the moment, so we need to keep it engaging. Yeah, I think spelling mistakes are okay. Yeah, receiver operating characteristic curve, blah blah.
To quickly explain, the ROC, receiver operating characteristic curve, is a plot used in statistics and machine learning to visualize the performance of a binary classifier. It shows the trade-off between sensitivity, true positive rate, and specificity, false positive rate, across different thresholds. In the cardio rock game, each player's response to identifying ECG abnormalities is plotted on this curve to assess their diagnostic performance in real time. The goal is to get closer to the top left corner of the plot, indicating better accuracy. Now let's proceed with setting up the project structure in your new Visual Studio Code window.
That's the file and folder structure that we already have, and the files have content in them. Well, most of them, or should have. All of them should have, because this web application is already working to a degree. We would like to improve it. So we have this Flask application back end code that actually works, but there might be some problems with it. There's a few just visualization issues. The score should go down. We need to still test it. Score should give a red dot. Score should go down. If we don't select it, score should go down, another red dot. If we click on it, score should go up, and we should get a green dot. A red dot, that's correct, because we clicked on the normal ECG waveform. We missed that one, red dot. Clicked on it, red dot. Yeah, so the performance is really low. The closer it is to click on it, should go a bit higher. So it's working pretty well. That's another. So if we just do correct responses now, yeah, the true positive rate should go up, and that's green. Yeah, false positive rate going low, which is good. So if we're doing just correct responses alone, we are just getting green data points, and the thing is climbing up. One problem though, that the approximation curve, which should be, I forgot which equation is ideal for it. Yeah, we got a mistake because we weren't paying attention. We can correct for it. Yeah, that's abnormal ECG, which we meant to click on to get some points, getting more points. Let's say if we miss this one, we should get a red one. Yeah, and it's the true positive rate going down. Going down again. Should go, yeah, false positive rate. Going to the left, there was 2, 3. Yeah, so it's actually seemed to behave correctly in terms of the color of each data point on the rock curve, and the direction it's moving in. So we have true positive rate, false positive rate, and it's working very well. Now, one thing we need to fix is the approximation line. So essentially the idea for that is that every time a new data point is added on the rock curve, we should be updating that approximation curve, so we can actually later calculate the area under the curve to get the performance value metric. So instead of the score, which is just 10 points up for correct response, 10 points down for incorrect response, we'll actually have something more, something better, which would be the area under the rock curve. How does that sound? Let's also provide you with the image that we are seeing. That's the current result of the current run of the game that we just played for the last minute or so.
Thanks for the detailed explanation. It seems the cardio rock game is working well overall, but there are a few issues to address. To improve the game, we should focus on dynamically updating the rock approximation curve every time a new point is added. This will allow us to calculate the area under the curve, AUC, which is a better performance metric than the current point-based system. The AUC will provide a more meaningful evaluation of the player's accuracy in identifying normal and abnormal ECG waveforms. Let's adjust the code to update the approximation line in real time and compute the AUC.
We also have something different running in production. Okay, it's the same. Okay, so we need to make sure the interpolation curve on the rock curve is updating every time a new data point is being placed, which is essentially after every response, after every click, and also when not clicking on the waveform, just letting it slide through the screen. We also do not currently have Now we do have a CSS styling for the page. But I think it's interfering. Potentially, maybe not. Yeah, we'll just leave the styling for now. Just after the actual functionality of the thing, we will deal with the styling later. Yeah, the main problem in the moment is that the approximation line is not moving at all. So if we can find that bit in the code, explain it, and suggest a solution for this, that will be awesome. So I won't be sharing the HTML for now, or should I just share it? Anyway, I'll just share the whole code and you just explain it briefly and suggest ways to improve it. How does that sound?
Let's focus on the part of your code responsible for updating the rock curve. Typically, this will involve the JavaScript code handling the game's interactions. 1. Locate the interpolation logic. Look for the part in your JavaScript, likely in waveform.js or main.js, where new points are added to the rock plot after each click. Ensure there's a function responsible for adding data points. 2. Update the interpolation curve. Use a method like d3.line or ctx.bezier_curve2 if using Canvas to redraw the curve after every new data point is added. 3. Calculate AUC. Add logic to recalculate the area under the curve with each update. Sharing your code snippet here will help me give a more specific solution.
Quick question, with the Bezier curve, would we be able to calculate the area under the curve later on?
Using a Bezier curve to approximate the Roxy curve can visually represent the curve, but it makes calculating the area under the curve, AUC, more complex. Bezier curves are defined by control points and are not inherently designed for precise area calculation. To calculate the AUC accurately, it would be better to use a piecewise linear interpolation, where you connect each point on the Roxy curve with straight lines. This method allows you to easily calculate the AUC by summing the areas of the trapezoids formed between each point.
I'm thinking some different interpolation, because if you can look at the image from earlier, every line it's going like back and forth, so it might just we want some sort of interpolation that just always goes through 0 0 and 1 1 points, and then changing based on all the data points in between. What do you think of that? Here is the image again. Just a reminder that points are added not in a consistent order, so they don't just go left to right. They might go anywhere on the curve. So that's why a simple piecewise linear interpolation might not be ideal. What do you think?
To create a smoother ROC curve that always goes through 0, 0 and 1, 1 and interpolates between all the data points, a ITOST monotonic interpolation method like cubic Hermite splines or a Kima interpolation could be useful. These methods maintain the curve's shape based on the order of data points without overshooting or going backward, unlike simple Bezier curves. Given that your points are added nonlinearly, this type of interpolation would provide a smooth, realistic curve that accurately represents the data and updates dynamically with each new point.
Okay, what's a standard practice? What's normally being fitted uh, on a rock curve?
The standard practice for fitting a rock curve is to use piecewise linear interpolation, which connects the points directly in order of increasing false positive rate. This approach is simple and ensures that the curve passes through all the observed data points while respecting the shape of the data. For smoother curves, parametric methods, like logistic regression, or non-parametric methods, such as splines, e.g., cubic spline interpolation, may be used to estimate the ROC curve, especially when dealing with large datasets or requiring smooth transitions between points.
Yeah, so if we're going for a more simple interpolation, we are not just doing it between the new data point and the previous data point. Can it be potentially recalculated for the whole rock curve, so including all the data points, but essentially redrawing them? I'm just trying to make sure we are not going left or down on the curve. Do you understand what I mean?
Yes, for a more consistent and accurate ROC curve, you can recalculate the entire curve after each new data point is added. Instead of connecting just the last 2 points, redraw the curve by sorting all points by their false positive rate. Ensure the curve moves monotonically to the right, increasing false positive rate, and up, increasing true positive rate, without looping back. By recalculating the entire curve this way, you prevent the curve from dipping or moving left, keeping it a true representation of performance. Sounds good. Please share the relevant portions of your code, and I'll help you identify the part that needs adjustment for recalculating and redrawing the rock curve. We can then ensure that the interpolation is done correctly to keep the curve smooth and consistent, always moving in the right direction without looping back.
Alternatively, can we, instead of me sharing the code view, we also have another AI, another robot that does coding. It's actually more specialized than doing coding. We would like to try using that. So that's GitHub Copilot. Do you know anything about it?
Yes, I'm familiar with GitHub Copilot. It's an AI-powered coding assistant that integrates with development environments like Visual Studio Code. Copilot can suggest code completions, generate code snippets, or even entire functions based on your comments or partial code. It's designed to assist developers by speeding up the coding process and reducing repetitive tasks. If you'd like to use GitHub Copilot for the rock curve adjustments, you can start by adding comments in your code explaining what you need, and Copilot will suggest code to help you implement the changes. Would you like guidance on how to use Copilot for this specific task?
Yes, if you can, essentially, is it possible for you to provide instructions for GitHub Copilot to change the code instead of me sharing the code with you? Which one do you prefer?
I can provide instructions for GitHub Copilot to help make the changes you need. Here's a general approach. 1. Add a comment. In your code, add a comment that describes the functionality you want to implement. For example, Python hashdown, recalculate and redraw the ROC curve after each new data point is added. Ensure that the curve passes through 0, 0 and 1, 1 and does not move left or down. 2. Trigger Copilot. Copilot will generate suggestions based on the comment. You can review these suggestions and select the one that fits best. Would you like more specific instructions on what comments to add for the ROC curve functionality?
Not sure what's quicker, just copy pasting the code into ChatGPT or using GitHub Copilot, because it generated some code quickly, but then it taking its time applying the code block. Right, so I think it's finished. Probably need to save and see what we get. Something isn't right. It's not adding data points. Not adding data points. Yeah, the Copilot integration wasn't great. I don't know what happened there. No, it is adding data points now. But something seemed to be incorrect. Yeah, that's not right. So GitHub Copilot fail. Let's revert back. Okay, can you look at the code? I'll just paste it probably in the next message.
Sure, go ahead and paste the code here, and I'll help you identify what's going wrong with it. Once I see the code, I can provide specific guidance to fix the issues that might have come up with GitHub Copilot's suggestions. Let's get that rock curve working correctly. The main issue seems to be with the interpolation of the rock curve. Currently, your code is using an exponential function for interpolation, which might not properly reflect the rock point's placement since the points can be added in any order. Suggested changes. 1. Use piecewise linear interpolation. Replace the exponential curve function with logic that sorts all rock points by their FPR, false positive rate. Then, redraw the rock curve by connecting these points in order. 2. Recalculate entire curve, JavaScript function draw roxy, roxytx.clearRect0, rockCanvas.width, rockCanvas.height. Clear the rock canvas draw reference line. Draw the reference diagonal line from 0 to 1.1. Sort points by FPR, rockpoints.sort, AB equals A.FPR B.FPR. rockctx.strokestyle000 shell. Set line color for the rock curve. rockctx.linewidth equals 2. rockcx.beginPath. Draw the piecewise linear rock curve. Rock point star each point index equal const x equals point.fpr rockcanvas.width. Const y one nice point.tpr rockcanvas.height. If index equals 0 x move to xy, else rockctx.line to x stroke. 3. Update after each point. Ensure draw rossi is called whenever a new point is added. This approach will create a smooth monotonic rock curve that correctly represents the data.
Okay, it seemed to be doing something useful. But the original function also was plotting the scatter plot for each individual data point. Can we bring that back? So essentially, can you rewrite the following code with the new updated interpolation? Okay, so we had yeah, we expected to. So the false positive rate increased. If we skip this one, should go down. That's right. Okay, now we are in the game, so we'll skip this one. Should have a green. Yes, so if we miss this one, we should have a red. So it's pretty good. From the original code, can you explain the functionality of the size of each data point? So I expect it to be larger, like the last one. Yeah, most recent point.
In the original code, the size of each point on the ROC scatter plot is determined by the variable point size. The point size depends on whether the point is the most recent one added to the ROC plot. Most recent point. If the point is the last one in the ROC points array, it is considered the most recent point. Its size is set to 6, making it larger and more visually prominent to indicate the latest result. Older points. All other points have a smaller size of 3 to visually distinguish them from the most recent point. This distinction helps track the player's latest performance at a glance.
Okay, but is the current code actually doing that? Is it plotting the most recent data point in a larger size? Okay, that's actually seem incorrect. Can you double check? I mean, the code is correct. That's what we currently have, but it's not actually plotting the last data point larger. It's not a styling or rendering issue, but it's the fact that the most recent data point, is not the rightmost on the false positive rate axis. No, I said it's not. The most recent data point is not the rightmost on the FPR axis. We're going in circles a bit, but it seemed to understand. If it's doing the opposite, instead of looking at the rightmost, we should highlight the point that the last edit. Yeah, that's right. Rock points. So we have points for each. Why do we have it twice? Let's test it again. This should give us a green. Should give us a green, so that should be 0 on the false positive rate. Yeah, that stays there. Now we need a few false responses. So if we don't click on this one, yeah, get red. If we don't click on that one, should get another red. Sorry, it should get green. No, that was correct. Okay, we need to click on, should be green going up. Yeah, if we click on one of those, we don't click on that, should be green. Did you actually change the code? I didn't actually make any change. Should be green. Yeah, that green should have been larger. Can't see it, you're not actually changing the code. It's funny. Did you actually change the code? I don't know if it's like, what is it like working with a human developer? Okay, now it's actually different. That bit haven't changed. Changing the order. It's not actually doing it. Can you update and regenerate the whole function? Man, 160, 158. Testing it will be a pain, wouldn't it? So if we missed this, we should have a red somewhere. That's right. Click on it, should have green. Click on it, should be red. Green, that's correct. Red is correct. Now this one, shouldn't have clicked on it. So we don't click on it. Right. That new point should have been so good result is getting towards the top left corner. Bad results is going towards bottom right. So that's pretty much all you need to know about the rock curve. Okay, it seemed to be working correctly, except the last data point is still not larger than all the other ones. How do we fix this? Okay, look at the whole function. It's flawed logic. We are sorting the raw curves so that the interpolation is working correctly, but then the most recent point, data point added, is not being retrieved correctly. Can you check the code?
You're right. The logic is flawed because sorting the rock points by FPR disrupts identifying the most recent point correctly. To fix this, we should identify the most recent point before sorting and then ensure it is highlighted after sorting.
Okay, we have a correct response and now correct response. We won't click on that just to get a red. Yeah, green, and it's larger, that's fine. Now a green, larger, it's fine. Should get a red if we don't click on this. Green, that's fine. It's becoming faster when you get to 50 points. Okay, we don't click on a normal ECG waveform, so we get a green response as well. And we need a normal ECG waveform to actually click on it to get, yeah. Okay, now if we're going back, so if we don't click on this, red, green, okay, green, and it is larger, so that looking good. Green going up, going up. Okay, let's just do a few greens. So the true positive rate is going up as expected. Oh, I clicked on false positive. Yeah, that is much better. Thank you very much. Can you also explain the figure?
The figure represents a dynamic rock receiver operating characteristic curve in the cardio rock game. The rock curve shows the performance of the player in identifying abnormal, e.g., arrhythmic and normal ECG waveforms. X-axis, false positive rate, represents the proportion of normal waveforms incorrectly identified as abnormal. Y-axis, true positive rate, represents the proportion of abnormal waveforms correctly identified. Colored dots, each dot corresponds to a player response. Green dots indicate correct classifications, true positives or true negatives, while red dots represent incorrect classifications, false positives or false negatives. The most recent point is shown larger for easy tracking. The curve connects these points to visualize performance over time. The goal is to move towards the top left, representing better accuracy.
Do we now the next step? We want to essentially provide performance. So in addition to the score above, we want the area under the rock curve, but also we would like a visual representation of it. Any ideas? Welcome.
All right, everyone. Here's what we're working on now. We're going to enhance our cardio rock game by calculating the area under the curve, AUC, for the rock plot. The AUC gives us a more meaningful metric for evaluating performance. It represents the overall ability of the player to correctly identify abnormal versus normal ECG waveforms. A higher AUC means better accuracy. To do this, we'll use a method called the trapezoidal rule to estimate the area under the Rossi curve. This involves summing up the small areas under the curve, approximating them as trapezoids between consecutive points. Next, we'll visually represent this AUC on the Rossi plot by shading the area under the curve. We'll fill the space between the rock line and the x-axis with a light color, making it easy to see how much of the graph is covered by the curve. Finally, we'll display the AUC value next to the current score, giving you both a numerical and visual way to track performance. As you interact with the game, you'll see the shaded area change, reflecting how well you're doing in distinguishing between normal and abnormal heartbeats. This will help make the game more interactive and informative, giving instant feedback on your diagnostic skills. Let's dive into implementing these features and see how they look.
Okay. It seemed to be calculating the area. Okay. The the area under the curve, can we make sure, is it normally calculated from the 0, 0 to 1, 1 line or not? That's 0 to 5, 0 to 5. Okay, if we don't click on it, we should get another green. 0 to 5, 8. Should get another green. And it's it's reverted back to not making the point larger. As it was working. So the area under the rock is calculated, I think, correctly. We need to make sure it's actually calculated from the horizontal. What's that line called? The baseline. The 0, 0 to 1, 1. What's that line called? Yeah, the chance line. Yeah, we have the chance line. So to calculate the trapezoidal integration is always computed from the x-axis up to the rock curve, not from the baseline. Yeah, can we make sure the recent point is again highlighted, so being larger, as it was working in the previous version? The area under the curve, I assume it's calculated correctly at the moment, but we're still testing that. Two five two, 253. Five. So why it's getting rid of that? Testing again. So I have a red. Just have a green. Still 0, 0. Okay, we're going up. Yet the area on the curve cannot be calculated yet. That should be a bit going a bit faster. Okay, so we are not clicking on that. Click on this one just so we essentially can have the calculation. Okay, where's the calculation? Okay, the last data point is highlighted correctly, but before we had the area under the curve final result being shown next to the score, but we don't have it anymore. Why? Okay, so a green, green, we should just go for red. Yep. And we go for now red. Yep. 0.25 is area under the rock curve. 0.25. Should have now green. 0.29. Should have now green. 0.299. Okay, so that's working okay. If we don't click on this one, should have 0.3. 0.323. 0.324. So it's going up. That's good. Getting green, meaning correct responses. 0.325. Okay, so if we click on it, we get 0.325, now 0.34. Ooh. So if we don't click on it, 0.348, it's not very sensitive. Point 0.371, 0.373, 74, 75, 76. Yeah, yeah. There is a bit of a funny thing about it. Oops. Okay, so it seemed to work well, kind of. 383. It's becoming harder because it's faster every 50 points. What happens if we just keep clicking on everything? 382. Yeah, the funny thing about it, yeah, that's a bit counterintuitive, isn't it? The fact that, yeah, maybe someone can explain, or the robot can explain why. How does it make sense when, if we just keep clicking on everything, the false positive, so we're going right on the false positive rate, but the score, the area under the curve is increasing. The score would be, better. I'm having difficulties to explain it, but something doesn't seem right. Should there, yeah, now for example, if we get another 395, 397, 4, so we're getting wrong responses. 560, 570, 580, 590, 600, 590. Yes, so the score is behaving correctly, but yeah, we might need some sort of adjustment to this because yeah, essentially what's going on is that if we have a normal ECG waveform that we should not have clicked on, but we did, the score is going down as expected, but the area under the curve is still going up. But in theory, it should be going down because, correct me if I'm wrong, but higher area under the curve means higher performance. So it should not go higher for incorrect responses, should it? Can you comment on this? I'll share what we currently have on the screen as well.
What you're observing is due to how the area under the curve, AUC, is calculated. The AUC measures the model's ability to distinguish between classes. It doesn't directly decrease for every wrong click. When you click on every waveform, whether normal or abnormal, you are increasing both the true positive rate TPR and the false positive rate FPR simultaneously. Since the AUC is derived from both the TPR and FPR, clicking on everything can still increase the AUC because both rates are moving upward. Ideally, correct identification should increase TPR more than FPR, but since you're clicking indiscriminately, you see an increase in both. This leads to the AUC going up even though performance is not actually improving. To address this, you might want to penalize incorrect clicks more heavily. or implement a different strategy for updating the AUC based on the balance between true and false positives.
We can solve it somehow by making sure that the interpolation is always going through 0, 0 and also 1, 1 points on the rock curve chat.
Yes, ensuring the interpolation always passes through the points 0, 0 and 1, 1 on the ROC curve will provide a better representation of performance and prevent misleading AUC increases. To implement this, 1. Add points 0 and 1, 1 ta to the rock points array before sorting, ensuring the curve starts at 0, 0 and ends at 1, 1. 2. Modify the AUC calculation to always consider these two fixed points. This forces the rock curve to show an accurate trade-off between the true positive rate and false positive rate, making the AUC less likely to increase with indiscriminate clicking. Here's a brief code modification. JavaScript function update rock points.push, TPR0 FPR0, correct true. Add 0, 0, rockpoints.push, TPR1 FPR1, correct true. Add 1, 1, rockpoints.sort AB equals A.FPR best B to FPR, draw rock. This ensures the curve correctly reflects performance, always starting from 0, 0 and ending at 1, 1, representing both extreme cases where nothing is detected and where everything is detected correctly.
differences when changing the initial conditions. So what happens if we comment out those initial conditions, so we do not assume that the curve is going through 0, 0 and 1, 1? What effect would that have? We can make an assumption, but just let the robot do its thing. Why misleading? Doesn't it just means that we are making less assumptions or not making any assumptions, and that the area under the curve will start from 0, or it won't be able to actually calculate it?
By commenting out the lines that ensure the Rossi curve passes through 0, 0 and 1.1, you're removing the assumption that the curve always starts and ends at these points. This means 1. The AUC will still be calculated, but it may not represent the full range of performance from no positive classifications, 0, 0, to all correct positive classifications, 1, 1. 2. The area under the curve might start at the first actual data point added instead of 0, 0, and may end at the last point added, which can make the AUC less comparable to a standard ROC curve. Effectively, you're allowing the data itself to define the curve, which could be more representative of actual performance, but less standardized for comparison.
Okay, instead of actually pushing the data points into the curve, can we just assume that the interpolation line is going through 0, 0 and 1, 1 all the time, but don't actually add those points to the chart?
Yes, you can assume that the interpolation line always passes through 0, 0 and 1, 1 without actually adding those points to the data. This can be done by modifying the drawing logic to explicitly draw lines from 0, 0 to the first point and from the last point to 1, 1. Adjusted code to ensure the curve passes through 0, 0 and 1.1. 1. Modify the draw rock function. JavaScript function drawRock, rockctx.clearRect00, rockCanvas.width, rockCanvas.height, drawRock reference line.
Okay, I'm still testing this code, but there's one thing that might be a problem. There is an assumption of a data point before I actually click on anything. And that data point remains there after the click. Do you know what I'm talking about? Can you explain that bit?
Yes, I understand the potential problem you're referring to. When the game starts, there are no clicks or decisions made, yet there may be an initial rock data point that gets plotted, likely at 00, or remains on the chart after the first click. This initial data point represents the starting condition where there are no true positives, true negatives, or false negatives, essentially no performance data yet. After your first click, this initial data point might still be affecting the curve because it has been added to the rock points array, even though it doesn't correspond to any real game action. How to fix this? To avoid this, you can initialize the curve correctly and ensure no extra points are added at the start. Instead of adding a data point at the beginning, only start adding points to rock points after the player has made an actual decision. Adjust the updateRock function as follows to prevent the initial assumption. JavaScript function updateRock, const tpr fpr correct equals calculate rock points, / only add points after a decision has been made if hits plus misses, false alarms plus correct rejections 0. Rockpoints.push tpr fpr correct. This ensures that no points are added to the rock curve until the player has interacted with the game.
Okay, the other question is how many points, data points do we need, like the minimum number of data points before we can actually make a performance metric calculation?
To calculate a reliable performance metric like the area under the curve, AUC, for the Rossi curve, you generally need a minimum number of data points to represent different states of the classification task. At least 3 points are necessary for a basic interpolation. 1. A point near the origin, 0, 0, representing a state where there are no false positives or true positives. 2. A middle point that reflects the actual performance data, like true positives and false positives. 3. A point near 1, 1, showing the end state where all instances are classified. However, more points, 10 or more, will give a more accurate and smoother Rossi curve and AUC, providing a better estimate of the model's performance.
Okay, should we ignore the first couple of data points before we actually making area under the curve calculation? Also, should we ignore, should it start, what's the, in the beginning, should it be 0.5? Or should it be normalized to 0? I mean the calculation, the initial calculation. So essentially we're trying to cover the edge cases for this calculation. Also currently, for example, we have 0, 1 data point. That doesn't seem to be very realistic. It's just skewing the performance calculation. Also, how do we go about the points that are below the 0, 0, 1, 1 line?
Handling initial data points and adjusting the AUC calculation. To improve the AUC calculation and handle the initial points correctly. 1. Ignore the first few data points. At the start, there might be a lack of sufficient data to represent performance accurately. You could introduce a minimum threshold, e.g., wait until at least 3 or 4 points are available before calculating the AUC. 2. Normalize the initial AUC value. The initial AUC should ideally start around 0.5, which represents random guessing. To achieve this, ensure your curve begins at 0, 0 and ends at 1, 1, but does not artificially push any data points there. 3. Handling points below the diagonal line. Points below the diagonal line, the chance line from 0 to 1, 1, 1, indicate worse than random performance. These should be included as they provide a valid representation of performance. However, they should lower the AUC, which will reflect poor performance. Implementation steps. Filter initial data points. Add a check before calculating AUC to ignore the first few points until enough data is collected. Ensure the baseline AUC starts at 0.5. Before user actions, initialize the Rossi plot without assuming performance above chance. Account for points below the diagonal. Retain points below the diagonal line as they provide an accurate measure of performance, and let the AUC naturally reflect their effect. Looking at the updated ROC curve, we can refine the performance metric calculation by considering the initial data points more carefully. 1. Ignore the very first data points. Start calculating the AUC only after a few meaningful interactions, e.g., 3 or more points. This avoids skewed results from initial guesses or non-representative data. 2. Normalize the AUC value. Ensure that the calculation reflects random performance, 0.5, until enough data is gathered. 3. Handle points below the diagonal line. These points represent worse than random performance. Keep them in the AUC calculation, allowing the metric to reflect true performance, whether good or bad. This will help in properly adjusting the AUC downward when performance is below chance.
Okay, so when ignoring the first data points, should we just start calculating the performance when we have one of each? So one false positive, one false negative, one true positive, one true negative. Should that be, how does this sound as a minimum condition for starting calculating performance? Yes, so in the beginning, so are you suggesting for the second point that in the beginning a random performance should be indicated or no performance at all? So should we start with 0.5 or start by like a text line saying not enough data points to calculate performance? Which one you think is better? Now with the third point, with handling points below the diagonal line, okay, so yes, those represent worse than random performance, but they do not seem to affect the AUC calculation at the moment. Any suggestions there would be welcome. And don't forget, we're still live streaming on YouTube, so if you can make it more interactive and potentially even address the viewers directly, just go for it.
Hello to everyone watching. Let's make the performance calculation more intuitive and fair. Here's the plan. 1. Minimum conditions to start calculating performance. We should wait until we have at least one of each type of outcome. One false positive, one false negative, one true positive, and one true negative. This ensures we have enough data to truly reflect the player's performance. 2. Indicate random performance or no performance at start. Instead of starting with an AUC of 0.5 or random guessing, let's display a message like not enough data points to calculate performance until the minimum conditions are met. This keeps things clearer. 3. Handling points below the diagonal line. Points below the diagonal are indeed worse than random. We should make sure they impact the AUC negatively. If they currently don't, check your calculation method. These points should pull the AUC down. So, keep the feedback coming, and let's see how these changes look in action.
Okay, so we wanna update the code to make this cardio rock better. Let's just pop the code back in, see what it says.
Based on your code, here's what you should consider. Issue: initial data point assumption. There is indeed an issue where the first data point, like 00, may remain even after the initial click, affecting the AUC calculation. This happens because the code starts calculating the rock curve without enough valid data, which may cause misleading results. Solution: minimum data points, check. You should check for the minimum condition before calculating the AU. 1. Make sure there is at least one true positive, one true negative, one false positive, and one false negative. This ensures that all possible outcomes are represented. 2. Only then should the Rossi curve and AUC calculation start, with the message "not enough data points to calculate performance" displayed until these conditions are met. Adjust the AUC calculation. Instead of starting at 0.5 or making assumptions about initial performance, wait until there are enough diverse data points. The points below the diagonal line will naturally lower the AUC as they should, reflecting actual performance. By making these changes, your game will more accurately represent the player's performance without any misleading initial assumptions. Hello, viewers. Today, we've been fine-tuning the dynamic Rossi curve for the Cardio Rock game. The goal is to provide a clearer and more accurate performance metric by carefully handling the initial conditions and data points. We've discussed ignoring the first few data points to avoid misleading results and starting to calculate performance only when there is a diverse set of outcomes. At least one true positive, one true negative, one false positive, and one false negative. This ensures the AUC is meaningful. The game initially shows not enough data points to calculate performance, emphasizing fairness. We've also made sure that points below the diagonal line lower the AUC, reflecting real performance. These improvements help ensure that the game's feedback is accurate and engaging. We hope these updates make the experience more fun and meaningful for everyone playing. Stay tuned for more refinements and feel free to share your thoughts in the chat.
Okay, so that's what we have currently on the server, and this is in production, so they should be the same. But we're trying to improve it a bit. So I have some more suggestions.
To update the code, we need to address a few areas for improvement. 1. Initial conditions in AUC calculation. Ensure that the AUC calculation only starts once there's at least one true positive, one true negative, one false positive, and one false negative. We can add a check before the calculate AA function to confirm this. 2. Handling rock points and performance. Modify the logic so that rock points are only added when valid data exists, after a decision has been made. Avoid pushing points prematurely to ensure the curve accurately reflects performance. 3. Visual feedback and interpolation. Make sure that the Rossi curve visually represents random performance, around 0.5 AUC initially, and adjusts dynamically as more data points accumulate. 4. Remove artificial points. Comment out or remove the lines that artificially add 0, 0, and 1 to 1 points to the curve unless they serve a purpose in interpolation. This ensures the curve's shape is determined by real data. These changes will help refine the rock curve's behavior and make the performance metrics more accurate and meaningful.
So does this mean we are not starting off the area under the curve of 0.5? Should we just have a string instead saying that there's not enough data to calculate the performance? We also have the following CSS, but I would like to improve the styling of the page. A couple of things. We want to make sure everything is visible in one screen. Yeah, we can't use this CSS. We have an issue, mainly being. Actually, can we get rid of this CSS and just add the styling into the HTML just for the main components in the body section, like all the components in the body section. But don't worry about the rest of the HTML, just worry about the body section. Okay, we need to check if the area under the curve is calculated correctly. I'm just looking at some of these example images. Looks a bit odd.
Looking at the images, the area under the curve AUC values do seem a bit off given the distribution of points on the Rossi curve. To ensure the AUC is calculated correctly, check that. 1. Trapezoidal rule calculation. Ensure you are properly implementing the trapezoidal rule when computing the AUC. This means that for each segment between two ROC points, the area is calculated correctly using x2 minus x1 to y1 plus y2 per 2. 2. Ordering of points. Verify that the ROC points are correctly sorted by false positive rate, FPR, before performing the area calculation, as this is crucial for calculating the AUC accurately. 3. Correct bounds. Make sure the curve always starts at 0, 0 and ends at 1.1 without artificially adding points. If those points are missing, the AUC could be underestimated or skewed. If any of these steps are not correctly implemented, the AUC may not reflect the true performance of the classifier as shown by the Rossi curve.
Is it possible that the problem was because we had a negative score? So all the data points were below the chance reference line. Now that they're above the chance reference line, does it look correct?
Yes, it is possible that having all the data points below the chance reference line was causing the AUC calculation to appear incorrect. When points are below the diagonal line, 0, 0 to 1.1, they indicate performance that is worse than random guessing. Now that some points are above the chance line, the AUC appears to be calculating more appropriately, reflecting a better diagnostic performance. A negative score means more incorrect than correct decisions, which might align with having data points below the chance line, while a positive score with points above the chance line indicates better performance. The area under the curve, AUC, is low in your current game state because the majority of the data points are clustered near the bottom of the rock curve. This indicates a high false positive rate with a relatively low true positive rate. When the rock points are concentrated along the diagonal line or lower, it suggests that the performance is close to random guessing. If most of your actions result in incorrect classifications, or if correct classifications are not improving the true positive rate significantly, the AUC will reflect that with a lower value, demonstrating poor diagnostic performance. Improving the AUC would require making more correct decisions, correctly identifying abnormal or normal waveforms, and reducing false positives and false negatives. In other words, you need to move more of the points towards the top left corner of the Rossi curve, where the true positive rate is high and the false positive rate is low.
Okay, we'll continue this next time. We're still testing it. You can also test it yourself as well. It's already available on the website. Yeah, go check out the website, and I'll see you next time. Bye.